Here's problem 3721. A thin sheet of plastic, n equal to 1.6, is inserted between two panes of glass to reduce infrared losses. Wavelength of light for the infrared is 700 nanometers. What thickness in nanometers is necessary to produce constructive interference in the reflected electromagnetic radiation? So we're going to put a thin sheet of plastic, index of refraction of 1.6, between two glass panes, index of refraction 1.5. And the idea is to reflect and hold in the infrared radiation so that we can keep the house even warmer than possible with the glass. So we want constructive interference of that wavelength. Now that wavelength, which probably is pretty close, well, it's just beyond the red, is going to do something like this, where we'll get constructive interference. It's going to reflect off the first surface with one phase reversal because we're going from a lower index to a higher index, and then that's going to be refracted inside to the plastic, where it'll be internally reflected off the second interface. Going from a higher index to a lower index, there'll be no phase reversal on that. And then it'll be refracted away from the normal as it comes back into the first glass. So there will be interference there, and we have one phase reversal. So in order to get constructive interference, we'll want that the path length, which will be twice the thickness of this plastic, will be equal to an integral number of half wavelengths, or a number of half wavelengths, so that we can get another phase reversal there and get constructive interference as a result. So within the plastic, the wavelength will be equal to the wavelength outside, or the wavelength in a vacuum, divided by the index of refraction of the plastic. So that's going to be equal to 700 nanometers divided by 1.6, and that is 437.5 nanometers. That's the wavelength inside the plastic. We already have one phase reversal, so we want that twice the thickness of the plastic is equal to another phase reversal, n plus 1/2 times the wavelength inside the plastic. So solving for thickness, we have the thickness is equal to n plus 1/2 times the wavelength, 437.5, divided by 2. And we're going to just simply choose m to be 0. We'll just find the minimum thickness necessary. And so what we have is 0.5 times 437.5 divided by 2. That gives me 109.4 nanometers. So that's 109.4 nanometers. That'll be our thickness of the plastic that will hold in the 700 nanometer light and hence keep the room warm. 109.4 nanometers.